Good morning everyone. Welcome to my YouTube channel Rudimentary. This is the first class of Engineering Thermodynamics and we'll discuss the basic concepts of Engineering Thermodynamics. This class will be extremely useful for all of you because we'll cover the basic concepts of Engineering Thermodynamics. Before discussing the basic concepts of Engineering Thermodynamics, first of all we should understand the genesis of thermodynamics. The name thermodynamics has its origin from two Greek words, thermi means heat and dynamics means power. Thermodynamics is the science of energy transfer which deals with the conversion of heat, work and other forms of energy and their effect on the physical properties of the substance. The laws of thermodynamics which have been formulated basing on the observations of common experience govern the principles of energy conversion. In fact, there are four laws of thermodynamics. They are your zeroth law of thermodynamics, first law of thermodynamics, second law of thermodynamics and third law of thermodynamics. All these laws we will discuss in the subsequent classes. An understanding of thermodynamics is incomplete without a proper understanding of the system, surroundings and boundary. Then what is a system? A thermodynamic system is that one upon which our attention is focused for analysis of problem from thermodynamic point of view. Anything external to the system is what we call your surroundings. Boundary is that which segregates the system from the surrounding. Then types of systems. The thermodynamic system may be categorized into closed system, open system and isolated system. Let us discuss these systems one by one. The first one is your closed system. Why it is called a closed system? Because it doesn't allow any form of mass interaction to take place with the surrounding. So neither mass from the system can enter the surrounding nor mass from the surrounding can enter the system. But a closed system does allow energy interaction to take place across the system boundary. That means energy from the surrounding can enter the system and energy from the system can also enter the surrounding. Then open system. It is called open system because it does allow mass interaction to take place between the system and surroundings. So in this case, both mass as well as energy from the surrounding can enter the system and from the system can enter the surroundings. Third one is your isolated system. Isolated system is that one which remains in which the system remains completely isolated from the surroundings. That means the surrounding has no bearing on the system. So neither energy interaction is allowed to take place nor mass interaction. But isolated system is purely a hypothetical concept and in real world there is no system which is an isolated system. Then we'll discuss about the control volume which finds extensive application in open systems. Introduction of control volume is very important in open systems like air compressor, and it is an arbitrary volume in space surrounding the open system like air compressor bounded by a surface called control surface. Pressure and temperature are very important parameters in engineering thermodynamics. Let us discuss about pressure, then we'll discuss about the temperature. Pressure is the force applied perpendicular to the surface of the object per unit area over which the force is distributed. In SI unit, the unit of pressure is Pascal, which is equal to 1 Newton per meter square. Then we'll discuss about the atmospheric pressure, the absolute pressure and the gauge pressure. So an atmospheric pressure, which is also known as your barometric pressure, is the pressure within the atmosphere of Earth. An atmospheric pressure is closely approximated by the hydrostatic pressure caused by the weight of air above the measurement point. The standard atmospheric pressure is 1,01,325 Pascal or 760 millimeter of mercury. All of us know that our Earth is surrounded by a cluster of air which we call your environment. The weight of the entire air column per unit area is what we call your atmospheric pressure. Absolute pressure is that pressure which is measured relative to the perfect vacuum. or your zero pressure. But what is a gauge pressure? When the pressure is measured relative to the atmospheric pressure, it is called your gauge pressure. That means in measurement of gauge pressure, the atmospheric pressure is taken as datum or reference. The gauge pressure may be positive, it may be negative, depending upon the absolute pressure. If the absolute pressure is more than the atmospheric pressure, then the gauge pressure is positive gauge pressure. If it is less than the atmospheric pressure, we call it a negative gauge pressure. This figure actually represents the relationship between absolute pressure, gauge pressure and atmospheric pressure. So there are two cases, one in which the absolute pressure is above atmospheric pressure. So in that case, the gauge pressure is a positive one. Second one, the absolute pressure is below atmospheric pressure. So in that case, the gauge pressure is negative one. Temperature is very important in thermodynamics. In fact, it is said that temperature is that factor which actually segregates thermodynamics from other sciences. Temperature is a thermodynamic parameter that determines the thermal state of the body, and it is associated with the ability to distinguish hot from cold. Hot body means that it will give off heat, and cold body means it will receive heat. The measuring instrument for temperature is called your thermometer. The concept about temperature would be more clear once we discuss the zeroth law of thermodynamics. Next thing that we are going to discuss is thermodynamic equilibrium. For a system to be in thermodynamic equilibrium, it has to achieve the following three equilibrium conditions. They are your mechanical equilibrium, your chemical equilibrium and your thermal equilibrium. Let us discuss these equilibriums one by one. First one is mechanical equilibrium. A system is in mechanical equilibrium when there is no unbalanced force between the system or between the system and the surroundings. Because if any unbalanced force exists between the system and the surrounding or between parts of the system, then certain spontaneous changes will take place. As a result, it will not be in mechanical equilibrium. For a system to be in chemical equilibrium, there should not be any chemical reaction between the components of the system or no transfer of mass from one part of the system to another. Third one is your thermal equilibrium. A system is in thermal equilibrium when there are no variations in temperature in the different parts of the system. Because if variations in temperature are observed, there will be spontaneous heat flow. As a result, thermal equilibrium will be affected. So when all these equilibrium conditions are satisfied, we say that it is in thermodynamic equilibrium. So then we'll discuss about the properties. Any system has certain characteristics by which its physical condition may be described. Such characteristics of a system are called properties of the system. And all the thermodynamic properties are broadly categorized into intensive properties and extensive properties. So let us discuss the fundamental difference between the intensive and extensive properties. An intensive property is that physical property of a system that doesn't depend on the mass of the system, like your density, your pressure and temperature. So irrespective of the mass of the system, density, pressure and temperature parameters will not undergo any change. But by contrast, an extensive property of a system does depend on the mass of the system, like your volume, internal energy. These are examples of extensive properties, because if you take a smaller mass and a bigger mass, they will have different volumes. Properties are the coordinates to describe the state of the system that we will observe once we study these things. Then we'll discuss about the state, process and cycle. State actually refers to the condition of a system at any instant of time and is defined by its properties. At a definite state, all the properties have definite values. Any change in one property means it has attained a different state. It is no longer in the same state. Any operation in which one or more properties of the system changes is called change of state. The succession of states passed through is called path of the change of state. When the path is completely specified, the change of state is called a process. Cycle actually refers to series of state changes such that the final state is identical with the initial state. So after undergoing a series of state changes, if you arrive at the same point from which you have started, that means you have attained the same properties from which you have started, then it is said to execute a cycle. Heat transfer and work transfer, they are central to the study of thermodynamics. So we'll discuss heat transfer and work transfer in details. Before studying heat transfer, we should know what is heat. Heat is actually a form of energy in transit, like work transfer, which is transferred across the boundary due to temperature difference. Heat transfer may or may not cause temperature rise. There is a misconception that heat transfer always leads to temperature rise. Heat transfer may be sensibility transfer, which is always associated with rise in temperature. It may be latent heat transfer, which is not associated with temperature rise. In that case, the heat energy is actually utilized to change the state of the substance, and there is no rise in temperature. The process which doesn't involve any heat transfer across the boundary is called an adiabatic process. The unit of heat in SI unit is 1 joule, and 1 joule of heat energy may be defined as the energy dissipated as heat when an electric current of 1 ampere passes through a resistance of 1 ohm for 1 second. There are 3 modes of heat transfer. They are your conduction, convection and radiation. Let us discuss the different modes of heat transfer one by one. First one is conduction. It is the heat transfer between two bodies due to direct contact. It is observed in solids or very thin layer of fluids, basically by molecular contact. The second mode of heat transfer is your convection. This is the heat transfer due to movement of the molecules. This is observed in fluids. Convection may be free or natural convection or forced convection. When convection takes place due to density difference, we call it a free or natural convection. When a pump or a blower is used to facilitate the convection process, it is called a forced convection. Radiation is the third mode of heat transfer, and in that case, heat transfer between two bodies separated by empty spaces or gases by electromagnetic waves. The heat energy we get from sun is through radiation, because there is a huge space between Earth's atmosphere and sun, which is devoid of anything, but still then we are getting the heat energy. Now I will take a very simple example to draw an analogy. Let us consider that a particular teacher of a school has been given the responsibility of distributing balls among the students belonging to his or her class. So he or she has 3 options. He can adopt 3 ways to distribute the balls. He or she would transfer the ball to the student nearest to him with the instruction that it is to be passed to the boy or girl nearest to him. And in this way, if the balls are distributed, this is analogous to your conduction. The second one he or she can adopt is to select some volunteers, and these volunteers should move around and distribute the balls. That is analogous to your convection. Third process he or she can adopt is to instruct the students to remain attentive, and he would simply throw the balls, and the responsibility of the students is to catch the ball. So in this way the balls are distributed. That is analogous to your radiation. As far as the sign convention followed in case of heat transfer to the system is taken as positive, and heat transfer from the system to the surrounding is taken as negative. This convention is universally followed. The area coming under the TS diagram represents the heat transfer in a particular process. Next important thing is work transfer. Before discussing the work transfer, let me tell you the sign convention which is followed in work transfer. Work done by the system is taken as positive and work done upon the system is taken as negative. This convention is also universally followed. So in mechanics, work is said to be done when a force is applied and it causes some displacement. And the magnitude of work is the product of force applied and the displacement caused. And the unit of work is 1 joule. When 1 Newton of force displaces the body by 1 meter, 1 joule of work is said to be done. But in thermodynamics, work is said to be done by system. Its sole effect on the surroundings could be raising of the weight. Here the raising of a weight is equivalent to the force acting through a distance. In real life, there may not be any raising of a weight, but still the work done by the system on the surrounding. So here it is important to observe that not weight is being raised in all the cases, but it can be reduced to raising of a weight. We can take a very simple example to describe that. We are having a motor which is driving a fan getting power from a battery. So in this case no weight is being lifted, but suppose that fan is substituted by a weight and pulley arrangement, then weight may be lifted. So this can be reduced to raising of a weight. Area coming under the PV diagram represents the work done in a process. These are very important for all of us to remember, that area coming under TS diagram represents the heat transfer during the process, and area coming under the PV diagram represents the work transfer during the process. Then we'll discuss about point function and path function. Point function is a function whose value depends on the final and initial states of the thermodynamic process, irrespective of the path followed by the process. It is also known as state function. All properties of the system are point functions. Examples are pressure, volume, temperature, etc. Point functions are exact or perfect differentials. So suppose at the beginning of the process the volume was 1 meter cube, and at the end suppose it has attained a volume of 3 meter cube. The change in volume depends upon only the final and initial volumes. So all the properties are examples of your point functions. Coming to path function, it is a function whose value depends on the path followed by thermodynamic processes, irrespective of the initial and final state of the process. Examples are your work transfer and your heat transfer. Already I have shown you that area coming under the PV diagram represents the work transfer, and area coming under the TS diagram represents the heat transfer during a process. So in both the cases, the path is important, not the initial and final one. So both the work transfer and heat transfer are your path functions. With this, I have given you sufficient idea about the basic concepts of thermodynamics. I sincerely believe that this class would be extremely useful for all of you. Again, I would request all of you to subscribe to my channel, Erudispace. Thank you all for listening to me.